Let's make a start. The agenda for today is going to be to go through the rates of change section in the Cambridge Unit 1 and 2 book. Basically, it's going to be essentially differentiation, or at the very least leading up to differentiation, calculus, that sort of thing. Particularly in the context of usually it's about things like particle motion, how a particle accelerates, has a particular speed or velocity, and where its position is with respect to some fixed origin. So the first of those chapters is essentially just being able to identify basic rates of change. So if we have a look at a screen share, one of the example sets they've given is essentially a sequence of different vessels that are holding some amount of liquid as water is being poured into it at a constant rate. That's what it means by being poured steadily. We're assuming that it's a constant rate at which the water is coming in. So if we were simply just to do the rate of change of volume with respect to time, the rate of change of water going in there with respect to time, that'll be constant for all of them because the flow of water is the same for all of them. What will be different, however, will be the height that the water is reaching within the particular container with respect to the same degree of volume. So all of these, I think it's supposed to be assumed that all of them will have the same volume for a certain different value of h, essentially. So if you consider beacon number 1, it's perfectly square and then it's got a neck on it. So essentially when you're filling this up, the rate at which the water will fill will be constant in the areas where the walls have constant width. So for instance, that's why you get this straight line as height increases linearly with volume, and then once it hits this neck of the beaker, suddenly it becomes much smaller or thinner, and therefore the height will raise much more rapidly with respect to the amount of volume of water that's going into it. We see a similar thing happen in part B. It's got triangular walls, which means that the height will be increasing at it'll be increasing at an increasing rate. So it won't be linear, it'll be slightly parabolic up until it hits the neck. There's a constant distance between the neck, and so for that reason it'll be linear from that point onwards. You can see there's a curve, and then it goes straight line from there. This one rounds out and comes back in, which is why at the beginning the height will slow down because it gets wider, 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 and then the height will increase because it gets thinner, thinner, thinner. So you can see the rate sort of wobbles a little bit like a cubic would. Then when it hits that neck, it goes constant. And then this is just that to the extreme, which is when it gets thinner, the rate increases. When it gets wider, or in this case it gets instantaneously wider, that's why you have these little dips every single time, because the overall width is changing. That's the basics of rates of change there. Where it comes in the context of particle motion is essentially you want to care about displacement, velocity, and acceleration. This one here is a displacement graph, d for distances. So distance, displacement, two sides of the same coin. Distance is specifically amount of distance traveled, whereas displacement is your location with respect to some origin, which is why the way the book's written this one out is particularly poor, because it does say the word distance, but because it says distance from a fixed point, you have to consider that as displacement. Should I dive into the differences between distance and displacement any more than that? Or are you already familiar, relatively speaking?
Yeah, it's all good.
That's all good? Cool. So, what's going on here? How do we actually describe the motion? This being a displacement graph, there's really only a couple of things you can determine about it. One will be the actual displacements for any given value of time, and the other, depending on how complicated the graph is, could be the speed at which it's going. If we know that speed is distance over time, what we're essentially saying is velocity or speed is the derivative of your displacement. When it's linear, it's pretty easy to calculate because it's just one rate of change for the entire thing. When there's slopes, you have to be a bit more careful with how you handle it because you can't necessarily assume quadratic, even though you definitely could make it a quadratic. Like for instance, you could force the turning point to be at x equals 20, y equals 0, and then you could force the other point to be at 7, 10, and then just create a quadratic off of that. But unless the graph tells you it's quadratic, you kind of just use more fluffy words around it. Whereas at the linear, you can absolutely calculate these rates of change. Like from 0 to 3, you've got a run of 0 to 3, you've got a rise of 5 to 10. That's a speed of 5 over 3. That's easily calculatable. Horizontally speaking, you're talking no velocity because there's no change in displacement. That's easy. Here, you just got to sort of say it's gradually decreasing. You got to use a bit fluffier words. You can't use hard math on it. As far as crafting your answer, you're pretty much just going to say started at displacement 5, ended at displacement 10 over a period of 3 minutes at an average speed of 5 over 3 meters per minute. So you would kind of just touch on time, displacement, velocity for each discrete section of the graph. Anything to discuss further there?
All good.
Sweet. This is where you get into the rates of change stuff. This is pretty chill. We've done derivatives before. Rate of change of y with respect to x is just another word for derivative. So where is derivative negative? Well, that's going to be where slope is negative. So that's going to be between -3 and the origin. Slope's pointing down. You want to be exclusive of those values because negative does not include 0. Same thing with positive, does not include 0. So for positive, you're going to be negative infinity up until, well, sorry, not negative infinity actually. This one does have a cutoff. I just realized I have the answers down here. Yeah. So -5 up to -3, again, non-inclusive, and then from 0 up until 2, non-inclusive on the 0. That's that one. There's a whole bunch of questions on that. I think what we'll do first is probably get through the basic content there, and you can tell me. Or was that off mute for a reason?
Chris, if no one else comes, can we do probability?
Yeah, I'd say that's fine. I'll basically just finish up the lecture portion on this just so it can be on the recording and someone can watch it back and learn from it.
Yeah.
And then we'll get into probability. Yeah. Constant rate of change, we basically touched on this before. When you have a slope, you just take your 2 points and then you do the rate of change from that. So in this case, we have distance of 150 kilometers in total, which is why it ends at the y equals 150, 2 hours, so 120 minutes. What's your rate of change? Assuming constant speed, you're just doing rise over run. This one's more a proportional based thing. You could calculate them individually just by sort of eyeballing where they end up, although this one, you can't quite call that 60. You more so have to rely on these dot points here, which is what happens when speed is doubled, what happens when speed is halved, and you just sort of go from there. That's pretty much all that's happening there. There's nothing really too crazy. Average rate of change is also the same thing as what we just did there, except the graphs that you have might be a bit more complicated, but you're still just taking 2 points on a graph. You're doing the slope between them. So for instance, if you wanted to find the average rate of change, or average speed rather, from t equals 2 to t equals 12, you first need to figure out what the y values are at that point, draw a straight line connecting them, and then the slope of that line is the speed because it's a distance time graph. Same thing over here, same thing over here. Yeah, same thing there. And then lastly is your instantaneous rate of change. Now, one of the things they do in this chapter in particular is try to lead you into it, where they'll do the diff by first principles sort of thing, where you do your f of x minus f of x plus delta x, or I think they use h in some cases. Where's the thing? They're going to have it somewhere. No, they don't quite have it there. But it's basically going to be this equation here, where you take your 2 points and then you add a fixed value to it, usually a small fixed value in the horizontal direction, and you're basically just doing average rate of change over a very, very small domain. That's all this one is. Up until a certain point, of course, where if you want to stop approximating the instantaneous and start just getting it, then you would just do derivative of your value, provided you have the function, of course. All right, that's a speed round version of that. There's more direct-to-camera lectures of it, so if anyone wants to get into or learn any more detail of that, then there's pre-recorded videos on that. For now, let's have a look at probability. What did you want to have a look at within probability?
We started chapter 14.
Start at chapter 14. Is this unit 1 and 2 or unit 3, 4 book?
3, 4.
3, 4. Okay. Let's pull that up. Chapter 14, unit 3, 4. Binomial. Okay. So whereabouts would you like to start having a look? Just top to bottom, or?
Yeah, if that's okay.
Yep, top to bottom's fine. So maybe before I do that, how much of chapter 13 discrete was good? Was that like at a pretty solid level?
Yeah, it was all right. It was just the conditional probability part, which was a little.
Is that something that you're still like happy to work through yourself, or do you want me to touch on that as well a bit?
I think I could work on that myself.
Okay, cool. Because yeah, I mean, if conditional probability was the only bit that was tough there, then that's going to set you up nicely for chapter 14, because binomial fundamentally is just a subset of discrete. There's actually not a whole lot that's happening different in binomial. Technically speaking, you can use all of chapter 13 to solve all of chapter 14 stuff. It'll just take you a long time to do that. So what we're doing with binomial is essentially figuring out some shortcuts, provided that you're able to identify what a binomial experiment actually is. So let's have a look. Binomial. So what is binomial? Well, you have to essentially meet these 3 criteria. The one that matters the most as far as in VCE is, do you have 2 possible outcomes for your scenario? If you think about the coin toss, for instance, you've got head or tail. That's binomial. You don't really ever have to think about criteria 2 and 3. Technically speaking, yeah, they are important, absolutely, but you got to remember these are specific VCE questions written to test certain things. As soon as you can identify you've got 2 outcomes, you really don't have to sort of think that much further. But if you want to, the other 2 criteria are that repeated trials have to be independent. So basically, the scenario has to reset itself every single time you do a new trial. That's usually your like with replacement scenarios, because you're putting the balls back in the jar or whatever the context is. And probabilities don't change from trial to trial. That's technically different from number 2, but even though they feel the same thing. So those are the criteria around binomial. Is that part all fair enough?
Yeah.
Awesome. As far as some key terms for you to identify, things like replaced or returned, I kind of mentioned that one before. You've got to have the scenario reset itself every time, so things have to be put back where they belonged before you start the next trial. If you see the keyword independent, if you see this notation, it might even flat out just tell you it's binomial, in which case, yeah, there you go. And then this idea of fair trials, that's hitting criteria number 2. But okay, the way we calculate binomial, at least by hand, is always going to be some form of Bernoulli sequence. You might have to do one Bernoulli sequence in the context of calculating a single probability, or you might have to do multiple Bernoulli sequences back to back if you have to calculate a range of probabilities. This is on your formula sheet, although it's actually put in 2 separate places, where essentially they have, well, I'll start pulling it up, but in the meantime, have you actually seen what it looks like on your formula sheet?
Yeah.
Yeah, okay. Do you know where the 2 sections are? It's got like an NCR section, and it's got a, I think they call it the binomial coefficient, weirdly.
Yeah.
But yeah, as long as you're able to read what's on there, then you don't actually have to memorize what this is. You just need to know that n is number of trials in the experiment, and p is the probability of the desired outcome occurring. When it's a coin toss, it's kind of whatever. It's already 50-50. But as soon as those probabilities start to split, then suddenly you have to care about which one's actually desirable. We do have a coin toss example. So coin is tossed 5 times in a row. What's the probability of tossing 4 heads? All right, that's one specific number of heads, which is why you have a PR capital X equals little x scenario. When you have that kind of scenario, you're just doing one Bernoulli sequence. N is 5, little x is 4, P is 0.5. Expand out and simplify. Do you ever have trouble simplifying the factorial division?
No, that part's good.
That's good. Easy. If you have CAS enabled, then you just do binomial PDF. So you just want to give the number of trials, probability of success, number of successes. So N, P, and then little x. Easy enough to spot it on your CAS?
Yeah.
Sweet. As I said before, if you want to find a range of probabilities, you're going to have to do the addition of multiple Bernoulli sequences. There is one kind of condition where you can circumvent that, but in fact, in most cases you can circumvent it, but if you can't, then you have to kind of sort of bite the bullet and do it twice. I've got a little guide here, just making sure that you make sure you handle the inequalities in the right way. So any less than or greater than signs are exclusive, so you want to go one layer up or one layer down from the numbers given. Whereas if you've got the equal signs attached to them, then you just start with that. Like for instance, tossing 1 or fewer heads means inclusive of 1. Which is why you do x equals 0, x equals 1. You calculate them individually, add them together. On CAS, that's a binomial CDF. It'll be literally just one below the binomial PDF. This is what I was referring to earlier, which is sometimes you have to calculate a lot of Bernoulli sequences, or you could do complement probabilities instead. So basically, anytime you have an inequality around like x equals 1, that's probably your indicator that you can start using some the complement probabilities approach. As soon as you see some sort of greater than or less than, no, usually greater than 1 is the way that's going to work. You just flip it. Part of the reason is because it's easier. Part of the reason is because sometimes it's the only way you can do it. Because if you have an uncapped n, if n is just some generic whatever, we don't know how big n could be, you literally don't know where to stop your Bernoulli sequence. Tech active, you're fine because you can get around it, but there are more efficient ways than just guessing and checking your way through it. So let's see. Tech free, coin toss of 5 times, 1 or more heads. You don't really want to be doing x equals 1, 2, 3, 4, 5. You'd much rather be just flipping that to the complement probabilities approach and going from there. That's cool so far?
Yeah.
Okay. With CAS, this is where it gets a bit more interesting. Now, technically speaking, there is a CAS function for this. It's called the inverse binomial. I think the Casio has a slightly different notation for it. I don't particularly use it. I've been burned from it before. I can't quite remember how I was burned from it, probably because of the rounding, which is why I'm depicting it this way. Now, if you've used inverse binomial before and you find it okay, you haven't been, like, you can clearly see how you would round it from a particular circumstance, then by all means keep using it. I feel this is probably a better way of going about things because, one, you can handle it in a tech-free way. It teaches you tech-free skills. And 2, it's avoiding whatever it was that was bugging me about it, which I wrote this a while ago. I can't quite remember what the issue was with the function. But okay, what's this all about? We have our p-value. We're trying to find n, specifically the minimum number of games of n, to ensure winning at least twice is more than 0.9. These are usually pretty wordy, so it becomes really important to sort of break these down into what sections, or break them down into sections essentially. So probability of winning a game is 0.25. Cool. That's our p-value. Sorted. We can ignore that. Next up, what is the minimum number of games? Okay, cool. So we're trying to solve for n. Mark that down somewhere and move on to the rest of the statement. Ensure probability of winning at least twice. So PR, winning at least twice, x equals or greater than or equal to 2, is more than 0.9. So this thing is greater than or equal to 0.9. You'll see in a minute why I've used an equal sign instead. That's how you break down those kinds of questions. It's pretty wordy. How was that? Any good? If you're speaking, you didn't come off mute.
Yeah, all good.
Okay. So, what do we do from there? Well, like we would always sort of do, when your n is uncapped, the only thing you really can do is do a complement probabilities approach. Now, because we're doing greater than or equal to 2, when we do our complement, we've got to have both x equals 1 and x equals 0. And we do 1 minus those. So from there, all we're going to do is use our CAS to simplify each of these. So if you do NCR on the CAS with n, 0, that will actually solve itself. It'll cancel itself down. Same thing with m, 1. If you do the NCR on the CAS, it cancels itself down. So if simplifying that by hand is tough, just know that the CAS can help with it. The power of 0 is whatever. And then this, well, obviously you just sort of simplify down to just 0.75 as your base. This one, ever so slightly harder, still 0.75 as your base, but you've still got this 0.25 that's associated with it there. So if that's x equals 1 and that's x equals 0, we plug those into this spot. All right, so instead of saying 1 minus all this, we now say 1 minus all that. This is where the CAS comes in. So we want to be more than 0.9. Specifically, yeah, more than 0.9. Now, oddly enough, at least in the TI Inspire, was when I tested this the first time. If you put a greater than sign here, the CAS will just give up and it'll be like, nah, I'm not going to do it. So put an equal sign instead of the greater than sign. That will actually give you your two possible solutions that you're looking for. Realistically, you're only looking for one solution. One of those is obviously going to be bad. All right? N being negative, pretty bad. N being a decimal isn't much greater either, but we can actually get around that now by rounding it. Now, every time I've done this, you always round up. That's just always been how it's been. The more nuanced approach there is actually testing, right? So instead of just sort of guessing that you round up, which I've never seen you have to round down before, but just in case, just to be safe, what I would do is I would grab this and define it as its own function, and then just test the different values of n. So test n equals 14, test n equals 15. Which of those gives you a number that's greater than 0.9? Obviously 15 is the only possibility there. So those are fundamentals around solving binomial probabilities. We haven't looked at statistics yet. Was there anything in there you wanted to drill questions on?
There was like
I'll take it you're looking for something? Or...
yeah.
Yeah.
It was like 14B, like seeing if it's like positively skewed and like just the mean variance, standard deviation
Yeah,
stuff.
okay, cool. So it's the one bit that I didn't mention, which was all the statistics. Got it. Okay, cool. Let me pull those out. Discrete binomial statistics. Alright, so binomial statistics are actually pretty easy to calculate. A lot easier than doing the discrete versions anyway. You just need to know n and p from what we discussed earlier, and that's used for calculating all of them. So your mean is going to be n times p, your variance is going to be np, 1 minus p, and your standard deviation is going to be the square root of that, as always. So as far as finding those statistics, you just need to identify n and p. So for instance, 3 balls are selected, so n is 3, and then p is going to be dependent on what the random variable is. So in this case, it's x is the random variable tracking white balls, so the p that you care about is the probability of selecting a white ball. From there, calculating is chill. You just use those n and p's. You can also go in the reverse order. If you have mean and standard deviation, or mean and variance, you can go backwards and calculate n and p by just doing a simultaneous. So if mean is 4, then np is 4. If variance is 2, then np 1 minus p is 2. Two equations with n and p in it, simultaneously solve. There is also confidence intervals, although I'm pretty sure that's not actually in this book. More so, I'll put it in there because it appeared in someone's sack for some reason. So I'm assuming this one isn't something you're worried about. Yeah. Alright. So whereabouts, what kinds of questions are you looking to drill from here?
Could we do the like worded questions?
Yeah. So we're talking from 5 down?
Yeah.
Yeah, okay. Fair die is rolled 6 times. Find the expected value for the number of 6s obtained. Seems like a fairly straightforward question there. The wording is very similar to discrete. What do you think we're doing there?
N and p
Yeah,
times n and p.
that's it. So what's n and what's p?
N would be 6. P would be 1/6.
Easy. Smashed it. Alright, that's that. Find the probability that more than the expected number of 6s is obtained. So, I mean, we can say that 6 times 1/6 is just 1. That's pretty easy. So what does that do for us as far as solving for b?
Could we transpose the equation to find p?
Well, p is the probability of a specific outcome, of getting a desirable outcome. When you're looking for these kinds of probabilities, so finding probability of more than a certain number of things happening, that's not p, it's what your equation equals. So for instance, if I pull up the Bernoulli sequence, you've got the probability, and then you got p. P is going to be based on the scenario, so that hasn't changed. What's going to change is this this left-hand side here, what this is asking you to do. Is that clear enough?
Yeah.
Cool. So we're still going to have the same n and p for this. What we have to do is figure out what our probability statement is. Like, is it PRX equals n, or is it PRX greater than or equal to, or less than or equal to n? That's what we got to figure out. So probability that more than the expected number of 6s is obtained. Any thoughts on how?
Would it be probability x is greater than or equal to 1?
Sounding good so far. Let me just double check. So what?
Or would it just be like without the greater than? Like, would it just be like more? Like
Yeah,
just
it'll
I
just be
think
greater
that,
than.
yeah.
It'll say if it includes it, it'll say more than or equal to.
Yeah.
Or it might say one or more number of 6s. Yeah, those are the ways. But yeah, so we're going to knock that one off, and we're going to use we're going to use 1 specifically because that's what the expected value was. Yeah. So our goal is calculate probability x greater than 1. That's our target probability. Question now becomes, how do we do that? There's a couple of ways. One's much easier.
Could we use CAS?
Well, yeah, okay, that's even easier, sure. Yeah, so CAS, what would that look like on a CAS?
CDF?
CDF, yeah. You would do, what's your lower and upper bound?
Lower is 1.
Lower's 2, because we're not including 1, remember?
Oh yeah,
So yeah,
2.
the CAS will take whatever you put in there as inclusive, never exclusive. So yeah, lower 2 and then upper 6 for this one. But okay, CAS will be nice and chill. That's not so bad. Tech 3 though, much tougher, or at least could be much tougher. There is a simplification that I mentioned at some point. What could we do?
Could we use the equation?
Yep, Bernoulli sequence will be part of it. That whole equation, yeah. How do we make use of it?
Would we use it and then go to like could we go the 1 minus thing?
Yes, that's much better. 1 minus. So how do I write the 1 minus version of this?
Would it be 1 minus probability of x equals 1?
Close. Let me just show you the full array. So if we think about rolling a fair die 6 times, the sample size of that's going to be 0 through 6, because it's about the number of possible 6s obtained. You could roll anywhere from 6 6s to 0 6s. So x greater than 1 just means that you're looking at this section of the sample space. So the complement to that is going to be from here down. So we're going to end up needing to do not just x equals 1, but also x equals 0. Probability x equals 1 plus probability x equals 0. Is it clear why we need both of those?
Yeah.
Yeah, forgetting about 0 is a pretty common thing. So what I tend to do is, well, I don't usually draw it out, but I usually at least think in my mind, what is my full sample size, or sample space rather, and then you have to think backwards from that. But okay, so as for calculating these, you said it before, these are just individual Bernoulli sequences. Now, that's a lot of messing around. Do you ever have any trouble calculating the Bernoulli sequences?
No.
Okay, cool. So yeah, you're just doing 2 of those, 1 minus, and you should be fine with that then. Cool. Okay, question 6. Survival rate is 75%. 50 people who contract the disease. How many would we expect to survive? That's some pretty key wording around that. What's going on?
N would equal 50.
Yep.
Probability is 0.75.
Yep. What are we doing with those?
Would we just put in the equation?
Which one?
The Bernoulli one?
Okay, if we put it in a Bernoulli sequence, we need to know. So Bernoulli sequence is for calculating x equals a specific number of something or a range of things. What do we actually have here? What are we trying to actually calculate?
How many people would survive?
Yeah, how many is expected to survive? That's a keyword there. Expect. What does that start?
Also N times P.
Yeah, expected value. That's it. N times P. And I mean, that should also, this usually makes intuitive sense. Like, we chuck all these equations around things, but I think people are pretty intuitive around the fact that, you know, if I have 50-50 in head or tails and I toss 100 coins, I'm expecting 50 heads and 50 tails. Like, we don't necessarily need an NP equation to calculate that. We kind of just do it in our head. Same thing for here. 75% chance of a success, 50 people, so 75% of those should be the survivors. But okay, that's that. I talked about this one before. This one isn't really worded anymore. Do you still want to do these kinds of questions here?
Yes, could we do one?
Yeah, certainly. All right, let's have a look at 7. We've got a mean of 12, variance of 9. How do we get n and p?
Could we go NP equals 12?
Yeah, there we go. That's good. Mean equals np, so np must therefore equal 12. Yep.
And the variance is 9, so could we go 9 equals NP 1 minus P?
Exactly right. Yeah. Now, this is just a simultaneous.
Yeah.
We could do it if you wanted to, but I'm pretty sure you're fine with that.
Yeah, all good.
Nice. There is a second part to that, which is hence find probability x equals 7. So, assuming you have your n and your p, how do you find x equals 7?
We can use the sequence.
Yeah, Bernoulli sequence. Easy. Same thing with question 8. Oh, look at that. They actually are going to be doing some binomial, some, what do they call it again? Confidence intervals. Yeah. So this exists in literally all of the areas of study, confidence intervals. Plus or minus some number of standard deviations centered at the mean is going to account for approximately 68% of the area if you're doing plus minus 1 standard deviation, 95% if you're doing plus minus 2 standard deviations, and 99% if you're doing plus minus 3 standard deviations. We looked at this at some point when looking, well, in more detail anyway, when we did normal distribution stuff, which is what, in fact, you'll see later on in the binomial, maybe it is in normal distribution actually, where they basically say, hey, if your binomial has a big enough sample size, it looks normally distributed. But that's for later. Point being is that the only ones that really tend to matter are your plus minus 2 standard deviations. That's what's usually tested in, well, clearly in the book, but definitely in the exam. They'll do that one over any others. But okay, let's in fact, yeah, I'll just do a quick run through of this one. So we're told 80% of students attend public schools, 400 students are selected at random. What is a 95% confidence interval for the number of people who attend public schools? So a confidence interval just says that we are some percentage confident that our result is going to be somewhere between some lower bound and some upper bound. So for instance, when we go through and we calculate our mean, variance, and standard deviation, plug them into the confidence interval formula, we're basically saying that we're 95% confident that the number of students attending a public school in any particular sample is going to be somewhere between 304 and 336. That's how to actually interpret confidence intervals. Calculating them is just chill though. Just need mean, standard deviation, and well, do some addition and multiplication. That's all this is. So if we have a look at question 9, basically put, if you want to get your mean and standard deviation, you need to know your n and p. So what's n and what's p in this scenario? Question 9.
N would be 20.
Yep, that's it.
P would be half.
That's it. Yeah, it's 20, p is a half. Do you want to go any further than that, or is it clear that you do your mean, standard deviation, and then you do your plug-in?
Yeah, that's all good.
That's all good. Okay. it does say interpret the interval. So let's just say, for the sake of it, that our interval was 3 to 17. What does that actually mean if we had an interval from 3 to 17 as a result?
Would it mean that from 3 to 17 times there was a head obtained?
That's definitely part of it, yeah. So plus minus 2 standard deviations. The key thing missing from the explanation was how it relates to the plus minus 2 standard deviations.
So 95% of the time, 3 to 17 times, basically.
That's good. Yeah, that's a complete explanation there, correct. Which is, we're 95% confident that the number of heads is going to be somewhere between 3 and 17 if we toss this coin 20 times. Yeah, that's that. I think question 10 is going to be the same. P is 60%, N is 200, mean is standard deep. Yeah, okay, it's the same thing. Except now it's students and schools, which I think was my example, actually. In fact, it might have been the same thing. Hang on. No, I did 60% and 400 instead of... Sorry, I did 80% and 400. Anyway, same thing. Anything else from here you wanted to have a look at?
No, I think the rest is good.
Sweet. Okay. 14C is the find the sample size sort of scenarios. That's where you have to find n, which is where you mostly rely on you're doing your complement probabilities. Yeah, just for the fun of it, in case for whatever reason you forget about this, I'll show you a guess and check way if you have access to the CAS. That way you have at least another fallback strategy if you're like, oh, CAS is playing up on me. All right, let's have a look. So the goal is, okay, let's see. Probability of winning a game is 0.48. What's the least number of games that must be played to ensure winning at least once is more than 0.95? So if you wanted to sort of hack your way through this, you basically just go through your CDF and you keep testing different values of n. Sorry, that's normal. I should do binomial PDF. So the n is the unknown bit. The probability of success is 0.48. Lower bound is always going to be 1 because you're trying to win at least once. And your upper bound is going to be whatever you choose your n value to be. Basically, we're going to keep testing values of n until we get the number immediately before getting a target probability of 0.95. So let's say I chose n equals 10. What probability do I get? Well, that's way too high, so we've got to roll it back a bit. Let's try n equals 8. What do we get? Wow, geez, it's still really quite high. N equals 4. Still too high. N equals 2. 0.7. N equals 3. 0.85. So we can say that n equals 3 is basically what you're looking for there. That's the value immediately before getting 90%. Oh, sorry, I was looking at 90%, not 95%. Whoops. We're looking at 95%, which means n equals 4 was the one immediately after. So, sorry, we should test n equals 5 then to make sure that works. Yeah, okay. So n equals 4 was immediately before it, n equals 5 was immediately after it. Since you want to be above, you choose your n equals 5. That's a hacky way of going about it. It might honestly be faster, actually, if you do have the CAS. And you always do have the CAS for these, actually. Yeah. What do you think of that method? It is actually faster, I would say, than doing all the math that I showed you.
Yeah, I like this way better.
Yeah, yeah. It's definitely a hacky way, so I don't know how much working you have to show for these kinds of things. I'm not sure guess and check is an appropriate working. Well, sorry, I know it's not appropriate working. But yeah, in a pinch, you can at least get the mark for answer and then call it there. But otherwise, yeah, using a complement probability approach, even if you just say 1 minus x equals 0 equal or greater than 0.95 and then go from there, that should probably be enough to get you the second mark for your working. And I mean, if you have to do it tech-free, which you never do, you can solve it using logs because what you get is an exponential. Like for instance, if I show you some more detailed working out, normally you just have the x equals 0. That's an exponential, right? You got known base to variable power exponential, which is why getting that n on its own requires a log. But I've never seen this, at least in an exam scenario, have to require tech-free. It's pretty much always been tech active in an exam. Maybe a SAC might be different. Definitely you're not going to get this sort of thing in tech-free though. When you have x equals 0, x equals 1, you're actually just flat out not going to be solving that. Like, try to get this out on its own. In fact, it might actually be impossible to do that by hand. Pretty sure these are always approximate solutions, which is why putting a greater than sign broke it a little bit. Yeah. But anyway, don't worry about it because you can just use the guess and check method. All right, let's give that a shot then, just so you can practice that. Do you have your CAS on you?
Yeah.
Yeah, okay. So I guess just so you can be familiar with how to do your guess and check, try it on 1B. And let me know if you're having any trouble with it.
I can't see the screen share.
I can't see the screen share.
It's
Oh, that's really weird. When I
yeah, I can see it now.
Oh wow, hang on. So if I click that again, does that cover it up entirely? It does.
Yeah.
Wow. Okay. That was me pulling up the answer sheet so I could refer to it. I guess when it comes up in the front, it actually covers up the screen share, but doesn't actually show what's on it. That's weird. All right, well that's fixed now. Let's not do that again.
I got 15.
Let's have a look. Bit high should be 14 for minimum number of shots. So test your n equals 14 there. Do you get a number that's greater than 0.95 still?
Yeah, I get 0.956.
Yeah, so always when you think you have the number, just test the one immediately before it just to make sure. But yeah, makes sense why it should be 15 instead.
Yeah.
Cool. C is almost the same thing, except now your lower bound's going to be 2, so nothing really different. Before actually, instead of actually doing it, hypothetically, should n be bigger or smaller, would you expect for C?
Smaller.
Why smaller? Why do you say smaller?
Um, I don't know. I just thought it'd be smaller.
Okay, well, fair enough then. So basically, the only difference between the scenarios is how many times I'm hitting the bullseye. So basically, the scenario is I'm throwing a dart on a dart or shooter, whatever is happening. I'm shooting at a bullseye, and I want to figure out basically how many times in the first scenario, how many times I have to shoot at this thing before I actually hit the bullseye or have a decent chance of hitting it. Versus this time, I have to hit it twice. What do you think is going to take longer?
The second time.
Yeah, second time. So based on that, n should be higher, not lower in that particular scenario. Because we're asking more of the scenario, so we would expect to do more trials on it. Actually calculating it, of course, you'll get there and get an answer. Ends up being 22, just out of curiosity. So a little less than double. Because 14 double gets you to 28. So that's interesting. It's not exactly symmetrical. Doubling the requirement doesn't necessarily double the n that would take to get there. But yeah, that's those kinds of interpretations come up as like little 1 markers. They typically call them separator questions. They're probably a bit tougher than the question I just gave then. But being able to interpret this stuff is sort of good. In fact, what was it? There was one all the way in sampling and estimation they like to answer, which is, hey, if I change my standard deviation, what happens to the width of the confidence interval? And so interpretation plays a big role in that. But that's a later topic. That'll be the last topic you look at, actually. But okay, that's that. What else have we got here? Smallest number, winning at least once. Oh, hitting exactly 5 times. Interesting. So question 3, what do you have to modify to make this guess and check or otherwise method work?
Would we use PDF instead? Because
Yeah.
it's equal.
Yeah, that's good. PDF. You're still going to be toggling n, but you're only toggling it in one place now since you have no upper or lower bound. So you'll just be doing p equals 0.6, x equals 5, and just cranking n until it gets there. Nice. Exactly 3, that's PDF again, at least twice, CDF for lower bound 2. More than 1, 4. This is a bit of a weirder one where the wording looks weird, but more than 1 is related to the actual like x greater than or equal to 1. Oh, sorry, greater than 1, not greater than or equal to. And then at least 50. Alright. Still CDF though, but yeah. Yeah. All those are the same question now. And the good news for you is that 14D is nothing. This is just a bunch of nonsense about proving things. That's about it for the lesson, really. Was there anything in there you wanted me to briefly touch on?
No, I think it's all good.
Sweet. All right. Doing well. Crushing binomial. Continuous is just integrals, so nothing too crazy there, I'm assuming. And then we've already done lessons on normal and sampling and estimation, either if you want to watch the recordings of those or even the direct-to-camera ones that are scripted. They might also help ahead of time. And then you're almost done with content. How's that feel?
Yeah, good.
It's crazy, isn't it? So close. Oh well, here to support. I'll leave you to it.
Thank you so much.
No worries. Take care.